Assignment Discovery is breathing new life into the collection of elements known as the nonmetals.
First, we'll dive into an overview of these essential elements in Exploring the Nonmetals.
Then, we'll learn about new automotive technology in hydrogen, fuel of the future.
Next, we'll travel back in time to discover an evolutionary explosion in oxygen, from pollution to revolution.
Then, we'll uncover how an accidental discovery in ancient China still affects us today in sulfur, life or death.
And finally, we'll examine chemical processes in The Chemistry of Caves.
Elements that change our world, past, present, and future. Coming up next.
As you watch the first half of this program, keep these questions in mind.
What properties do the nonmetals share?
How do hydrogen and oxygen work together to create electricity?
The nonmetals make up much of the world around us. They are primary ingredients in many of the natural resources people still rely on today, and so are very important to modern civilization. What are some natural resources, and why are they important?
Water, trees, grass.
Number one would be petroleum.
Oil, that just helps us with our cars and making plastics.
Trees we use for making paper, and we write on paper and we print on paper.
Lots of people use wood to build our houses. If we want to make fire.
Trees develop oxygen for us to breathe, and water is something that we need to live.
Nonmetals are insulators or semiconductors, and their oxides are acidic. They are highly electronegative, meaning they will gain electrons instead of losing them. Nonmetals form ionic bonds with metals by gaining electrons or covalent bonds with other nonmetals. Hydrogen, a nonmetal, is a colorless, odorless, highly flammable gas. It is the lightest and most abundant element in the universe. Hydrogen is the main energy source for our sun. Two hydrogen atoms are fused together, forming helium and releasing light and heat energy. Carbon is a solid with several different physical forms called allotropes. It can appear as a dark, brittle material called graphite, or as diamond, the hardest natural substance known. Nitrogen, as a gas, is colorless, odorless, tasteless, and inert. Nitrogen makes up 78% of Earth's atmosphere and is an important component of many proteins and fertilizers. Oxygen is a colorless, odorless gas, abundant on Earth, and necessary for the support of many forms of life. Oxygen is formed primarily as a result of plant photosynthesis. Phosphorus has three main solid allotropes: white, red, and black. Because it is highly reactive, it is never found as a free element in nature. Pure white phosphorus ignites spontaneously in air. The red allotrope is used in matches. Sulfur, once known as brimstone, is a yellow crystalline solid. It was a main ingredient for medieval alchemists. Selenium is a gray nonmetal that conducts electricity better when exposed to light. It is also a trace element that helps the thyroid gland function, but many of its compounds are extremely toxic. there are far fewer nonmetals than metals on the periodic table. But nonmetals make up most of the Earth and its organisms. Because of their high electronegativity, the gaseous nonmetals exist naturally in a diatomic state. Hydrogen, nitrogen, and oxygen form molecules made up of two atoms bonded together. This molecule is much more stable than a single atom. Phosphorus, sulfur, and other nonmetals also form polyatomic molecules. Phosphorus makes pyramids of 4 atoms each, and sulfur exists naturally as a ring of 8 atoms. This tendency to form polyatomic molecules can be explained by taking a closer look at the periodic table. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is surrounded by an equal number of electrons. As the atomic number increases, generally so do the size and mass of the atom. As you read the periodic table from top to bottom, each horizontal line is called a period. This represents the number of electron shells the element's atoms normally have. For example, an atom of nitrogen has 2 electron shells, so it lies in period 2. And an atom of selenium in period 4 has 4 electron shells. Each of these shells can contain up to 8 valence electrons. As you read the table from left to right, the vertical lines of elements are called groups. Elements in one group have the same number of valence electrons in their outermost electron shells. These are called valence electrons, and they usually dictate how elements interact. The nonmetals are to the far right of the periodic table. Not including hydrogen, they span groups 14 through 16 and have anywhere between 4 and 6 valence electrons. Hydrogen is in group 1 above the alkali metals, but it behaves as a nonmetal in most circumstances. It has 1 valence electron, but its valence shell is complete with 2. The type of bond a nonmetal forms depends on its own valence electrons and on the type of element with which it is bonding. Generally, nonmetals will share electrons with other nonmetals in a covalent bond and take electrons from more electropositive metals in an ionic bond. Carbon, with 4 valence electrons, has the most flexible bonding properties. It usually does not form ionic bonds, but it is able to form rings or long chains by bonding with itself. This versatility accounts for the wide range in appearance of carbon's allotropes. Oxygen, with 6 valence electrons, will take electrons from metals to bond ionically. In fact, when any element is oxidized, it gives up electrons. Nonmetals may be a minority on the periodic table, but they make up the majority of the world around us. Did you know nonmetals are truly the basis of life? Hydrogen, carbon, phosphorus, oxygen, and nitrogen make up DNA, the molecule that encodes life on Earth. From these 5 basic elements spring all organisms.
The 21st century holds the promise of new technologies that will improve our lives. One of our goals is to find cleaner and more efficient ways of producing energy. Hydrogen may be the answer to a cleaner fuel for cars, but scientists are still experimenting with many different ideas.
What are some forms of alternative energy?
Some cars run off of biomass.
Hydrogen fuel cars.
Solar-powered energy.
You could either use normal solar energy with panels, or there's passive solar energy where you orient your house with like windows and make sure the sun warms the house itself.
Water power, wind power.
My engineering teacher said that he's going to try and put something in his car where he can just use corn syrup for energy.
Element number 1 on the periodic table is hydrogen. The atomic symbol for hydrogen is H. Hydrogen is a very light, odorless, and colorless gas that is extremely flammable. Hydrogen is the simplest element and the most abundant in the universe. Hydrogen gets its name from the Greek words hydor and genomai, which means to bring forth water, because when hydrogen is burned, it produces water. Hydrogen is classified as a nonmetal. It lies in the periodic table's first row, period 1. Each hydrogen atom consists of one electron that surrounds a compact nucleus, which contains almost all of the atom's mass. In the most common form of hydrogen, its nucleus has only one positively charged proton. Unlike all other elements, hydrogen has no uncharged neutrons in its nucleus. One negatively charged electron balances hydrogen's one proton. Hydrogen's electron is found in the single orbital shell that surrounds the nucleus, the sphere-shaped 1s shell. This single valence electron determines hydrogen's unique chemical behavior and makes hydrogen highly reactive. In this experiment, a partly filled plastic bottle contains hydrogen above water. When the water is emptied from the bottle, air, which contains 20% oxygen, rushes in to take its place. When a lit taper is placed near the bottle's opening, the hydrogen and oxygen ignite to project the plastic bottle through the air like a rocket. The products of this explosion are water vapor and a lot of heat. Hydrogen is a very important commercial element. It combines with numerous other elements to form chemical compounds that we use every day, such as water, table sugar, ammonia, and hydrogen peroxide. Liquid hydrogen is often combined with liquid oxygen to make rocket fuel. America's first mass-produced automobiles rolled off assembly lines in the early 1900s. Today's cars are much more efficient, more powerful, and more advanced. But most still use the same fuel as the cars of 100 years ago: gasoline. When car engines burn gasoline, they release carbon monoxide, nitrogen oxides, and other harmful chemicals into the air. These gases cause smog and acid rain, and many scientists believe they may also contribute to global warming. Gasoline is made from non-renewable fossil fuels such as petroleum, coal, and natural gas that take millions of years to form deep inside the earth. Once the current supplies of these fuels are used up, they are gone for good. Scientists the world over are working on finding alternative fuel sources for the cars of the future. Modern hybrid technology, which uses a combination of gasoline and electricity to power a car, is becoming popular. Hybrid cars are much more efficient than those using conventional engines, but they still rely on the same limited resources as gasoline-powered cars. So some engineers are working on ways to make cars run not on gasoline or hybrid electricity, but on the limitless resource of hydrogen. Hydrogen is the most abundant element in the universe. It makes up more than 90% of all the matter in existence. It is colorless, odorless, tasteless, non-toxic, and highly combustible. Hydrogen has been used to power rocket engines and make devastating bombs. But it is not the combustible nature of hydrogen that makes it a good possible fuel for the future. Instead, it is a basic chemical reaction that scientists have understood for over 150 years. The elements hydrogen and oxygen have a natural attraction to each other. Together, they form water, and when they combine, their chemical reaction releases electricity. This is the principle behind the hydrogen fuel cell. Originally developed for the Gemini space program in the 1960s, fuel cells combine hydrogen, the green atoms, and oxygen, the blue, to produce electricity. Inside the fuel cell, a platinum catalyst splits atoms of hydrogen into positively charged protons and negatively charged electrons. The protons pass through a membrane to bond with oxygen on the other side. The electrons are blocked by the membrane and must flow around it through an electric circuit to recombine with the hydrogen and oxygen and form water. When an electric motor is plugged into this circuit, the electron current is enough to power a car. The only waste product of the process is water. Hydrogen fuel cells have no mechanical parts, such as a transmission, do not operate at high temperatures, and do not need lubricating oils. So maintaining fuel cells should be easier and cheaper than traditional engines. Practical fuel cell cars are still a long way off. Today, it is about 20% more expensive to make hydrogen than a comparable amount of gasoline. And scientists must develop better ways to store hydrogen. Fuel cells are much larger and more expensive than traditional gasoline engines. And current gas stations do not deliver hydrogen to drivers. So most hydrogen-powered cars on the road today are prototypes or test vehicles. But improvements in the technology could one day solve these problems and provide a reliable, efficient, and clean-burning fuel source for centuries to come. Did you know? Towering pillars of concentrated hydrogen gas may be a type of star nursery. Until the Hubble Space Telescope began taking detailed pictures of deep space, such nebulae appeared as fuzzy specks in the sky. But the detailed color photographs show that these clouds are dotted with bright light, most likely young stars created from the hydrogen.
Air pollution in the form of excess oxygen presented a crisis for life on Earth billions of years ago. Today, we face another pollution crisis. Industry provides the modern world with advanced technology, but often it comes at the cost of environmental damage. Scientists are now searching for cleaner production methods.
What makes up the air we breathe?
What's in our air is whatever's around you. Like, there's dust and mold.
You have every gas type that's on the periodic table of elements.
Oxygen, carbon dioxide, nitrogen.
It's mostly nitrogen along with carbon, oxygen, and that's pretty much it.
Element number 8 on the periodic table is oxygen. The atomic symbol for oxygen is O. Oxygen is a colorless, odorless, tasteless gas that is non-flammable. Oxygen gets its name from the Greek words oxys and genomai, meaning to bring forth acid, because it was once incorrectly believed that oxygen was needed to form all acids. Oxygen is classified as a non-metal. It lies in the periodic table's second row, period 2. Each oxygen atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of oxygen, its nucleus has 8 positively charged protons, plus 8 uncharged neutrons. Oxygen has 8 negatively charged electrons to balance its 8 protons. These electrons are found in orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed among one orbital shell. Oxygen has 6 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The final 4 electrons are distributed among 3 lobe-shaped 2p orbitals. Oxygen is a highly reactive element, and the 6 valence electrons in its second-level shell influence how it interacts with other elements. In this experiment, a stream of pure oxygen is directed at a piece of burning charcoal, which immediately begins to spark. The abundant amount of oxygen helps support the combustion of the charcoal, but the oxygen itself does not actually burn. The sparks are small pieces of the glowing charcoal that break away. This reaction is commonly used in steel mills to heat molten iron and produce steel. Oxygen and its compounds are used in water purification, cement and steel making, and welding. Liquid oxygen can be combined with liquid hydrogen to make rocket fuel, and it is necessary for combustion. Oxygen is also required by most living things to breathe. Air pollution is a universal problem that affects the health of all Earth's inhabitants. It destroys the planet's protective ozone layer, and it contributes to many types of respiratory problems, and it has been linked to cancer and other serious diseases. In recent decades, people have become more aware of the dangers of air pollution, and they have made strides to make our air cleaner. But billions of years ago, the Earth's pollution problem was far different from the problems we face today. In our planet's early years, about 3.5 billion years ago, the atmosphere was made of carbon dioxide and methane gases. The first organisms to appear were various forms of bacteria. One group known as cyanobacteria still exists today and are photosynthetic, meaning they extract energy from sunlight. A main byproduct of photosynthesis is oxygen. The oxygen introduced into the atmosphere about 2.5 billion years ago was a serious problem for much of the life on the planet. It was lethal to many of the bacteria that existed at the time. Soon, the Earth's atmosphere was polluted with a deadly poison, oxygen. As some bacteria species died out, others adapted. These organisms began building up defenses to the oxygen-rich atmosphere and found that the element could be utilized to produce energy more efficiently. Over the next few million years, some bacteria evolved into more advanced single-cell organisms. These organisms contained about 1,000 times more DNA than any bacteria. And as organisms adapted to Earth's atmosphere, they gave rise to ever more complex, multicellular organisms. Eventually, the once deadly oxygen became a necessity for nearly every living creature on the planet. Earth's earliest organisms had adapted and helped turn oxygen pollution into a new opportunity for growth and life. Did you know? We've come a long way since life began billions of years ago on Earth, but not everything has changed. We still rely on photosynthesis to produce oxygen. In fact, marine organisms, including blue-green algae, a close relative of ancient cyanobacteria, continue to produce most of the oxygen in our atmosphere.
In the 9th century, the discovery of gunpowder forever changed the way people fight wars. Its profound impact changed the world, and those effects can still be felt today.
How has warfare changed over time?
The weapons are obviously different. Technological advancements with weapons, and now we have like new missiles and bombs.
Well, in the American Revolution, they would use cannons or something. Now if they really needed to, they would just use a nuclear bomb.
The whole face of combat has changed.
War seems to be more precise.
Once guns were invented, like warfare became less personal because you could shoot someone from really far away and not realize, like you wouldn't see them like die.
You have like computer-guided missiles where it's like everything's a lot more accurate. Sometimes you don't even have to send troops in. I mean, just fly over and then that's all you need to do.
Element number 16 on the periodic table is sulfur. The atomic symbol for sulfur is S. Sulfur is a yellow powder that has a pungent odor when it is heated. The name sulfur is from the Latin name for the element, which was known to the ancients and was once referred to as brimstone. Sulfur is classified as a non-metal. It lies in the periodic table's 3rd row, period 3. Each sulfur atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of sulfur, its nucleus has 16 positively charged protons, plus 16 uncharged neutrons. Sulfur has 16 negatively charged electrons to balance its 16 protons. These electrons are found in 3 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed among 2 orbital shells. Sulfur has 6 more electrons than neon. The first 2 electrons are found in the sphere-shaped 3s orbital shell. The remaining 4 electrons are distributed among 3 lobe-shaped 3p orbitals. It is these 6 valence electrons that determine how sulfur interacts with other elements. Sulfur exists in a number of different forms called allotropes. Here, the most common allotrope of sulfur at room temperature, yellow sulfur, is heated in a test tube using a propane torch. The sulfur first melts at 115 degrees Celsius and changes into a mobile orange liquid. Then, as the temperature rises above 175 degrees Celsius, a clear transformation takes place as the liquid thickens and darkens, becoming black and extremely viscous, almost like molasses. This is a physical change as sulfur atoms rearrange themselves to form long chains in a process known as polymerization. When the viscous molten sulfur is poured into water, it solidifies into a flexible, tangled mass known as plastic sulfur. Over the next few days, this plastic form will gradually revert back to its original hard yellow sulfur. Sulfur is used to vulcanize rubber, produce pesticides, and manufacture gunpowder and fireworks. It is also used to make sulfuric acid, which goes into fertilizer and lead-acid batteries. In the Middle Ages, the practice of alchemy was widespread. Alchemy was a chemical philosophy with 3 goals: to turn base metals into gold, a process called transmutation, to find the universal cure for all diseases, and to prolong life indefinitely. Monks in Europe searched for a philosopher's stone that would allow them to turn lead into gold. In China, emperors spared no expense in the search for the elixir of life. While most medieval alchemy proved fruitless, some alchemists did stumble onto unexpected and sometimes valuable discoveries. One occurred in China during the Tang dynasty in the 9th century. An alchemist searching for the secret to eternal life created a mixture that included sulfur, charcoal, and potassium nitrate, also known as saltpeter. While this new mixture did nothing to extend life, it did explode when lit with a flame. The Chinese alchemist had created gunpowder. The explosion of gunpowder is a simple reaction. Charcoal works as fuel, and sulfur is a stabilizer. The main ingredient is potassium nitrate, which provides extra oxygen, allowing the mixture to explode instead of simply burning. The Chinese attached bamboo tubes loaded with gunpowder to arrows to make rocket-propelled missiles. Now one soldier could do as much damage as a regiment. When gunpowder arrived in the West, Europeans immediately wanted to put it to work. They turned to bell makers to engineer an object that was strong enough to hold together when the black powder exploded inside. The cannon was born. Cannons were able to destroy defensive walls that had stood for centuries. Today, we live in a world changed by the advent of gunpowder, the ironic result of the search for everlasting life. You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
What properties do the nonmetals share?
How do hydrogen and oxygen work together to create electricity?
If you'd like to learn more about what you've just seen, go online or check out these books at your local library.
As you watch the second half of this program, keep these questions in mind.
How does a limestone cave form?
Why is it important to protect caves and cave formations?
Caves provide a unique environment. They have their own chemistry and their own ecosystems as well. Some animal species have adapted to extreme darkness and other conditions in caves.
Have you ever had to adapt to new surroundings?
I was actually brought up in England, and when I was about 12, I had to move back to America.
When I moved to from the Caribbean to America, I had to get used to this, for one, the cold weather.
Coming to a new high school was there just being a lot more kids.
I came from a Catholic school, born and raised, very religious, and when I came here there were people from all different cultural backgrounds, religious backgrounds, and it was a big cultural shock.
Many ancient peoples thought of caves as routes to the netherworld, a spirit world of shadows and ghosts. They weren't entirely wrong. Explorers dare this forbidding underworld today. Caves are a challenging frontier, a test of strength and skill. But the idea of caves as portals to another world lingers, luring us deep into the darkness below. These people are preparing to make a journey from our sunlit world to a more mysterious domain.
Light check. Everybody have backup lights on their helmets as well as their main.
They're space travelers. The ultimate destination is well beyond the Twilight Zone. They're all inbound for inner space and into the world of deep caves.
Kind of like being on another planet, but being with aliens, sort of, too. It's just a whole different way of life.
You don't panic. You need to overcome your fears. You need to realize that your training and experience will get you out of any situation that you're in.
Fear of the dark, fear of falling, claustrophobia, fear of being lost forever, fear of dying. Caves bring it all out, bring it all to the surface. There's a variety of cave types. Some of them are quite rare, like Fingal's Cave in the Scottish Hebrides. The cave is worn into an ancient volcanic deposit of basalt by wave action. There are ice caves, like Eisreisenfeld in the Austrian Alps. The interior is covered with ice crystal formations. Lava flows from active volcanic eruptions form lava tubes. Somewhat more common, they are among the youngest caves on Earth. The most common kind of cave occurs in rock that dissolves in acid, like these underwater caves in Florida. The rocks are marble, dolomite, and especially limestone, all containing calcium carbonate. The acids come from decaying plant and animal matter, or from petroleum deposits deep underground. No matter how they're formed, caves have drawn people in for more than 1 million years. They provided early primitive humans with protection from the elements and from predators. We no longer need caves for survival. So we go into caves for different reasons. Archaeologists enter to study artworks and artifacts left by prehistoric peoples. The cave environment can be a near-perfect archaeological site because the climate and chemistry often preserve artifacts for a long time. Geologists love caves because they're windows into the history of the planet. What's more, no two are alike. Each one is utterly unique. Cave formation is unusual. Acids form caves in marble, dolomite, and especially limestone deposits. Biologists go into caves because they're home to a unique ecological community. A single cave may house creatures that exist nowhere else on the planet. No matter the reason, each and every person who explores caves must face the dangers and challenges that any cave holds. And like the ocean, caves deserve great respect. Whoever underestimates them courts disaster. Today, we've developed show caves, which are for tourists. But wild caves remain the realm of explorers and adventurers. Cavers need experience and technique to survive in wild caves. The payoff can be the thrill of discovery, of entering a subterranean chamber where no one has ever been before. The full extent of the world below is unknown. Caves have been found all over the world. A few thousand have been explored to some degree, but these may amount to no more than 10% of the total. The cathedral chambers of Mammoth Cave, Kentucky, witnessed Native American explorers. The artifacts suggest they began visiting 4,000 years ago. What they were doing here is still a mystery. It may seem like a long time ago, but by the time the first humans set foot in Mammoth, the cave was already between 3 and 5 million years old. And its limestone was nearly 300 million years in the making. Mammoth Cave is the longest known cave in the world, with 356 miles of known passages, some running 600 feet underground. It's a three-dimensional system, with multi-level galleries monumental in size and scale. There's more undiscovered, unexplored cave out there, too. Estimates run up to 500 additional miles. How does a limestone cave like Mammoth form? What opened and emptied these spaces of rock and cut the walls with such precision? Though each limestone cave is different and has a unique history, the fundamental answer is always the same. Diluted acids flowing through underground deposits of limestone dissolved the rock and created a cave. This space began as solid limestone. Time and mild carbonic acid ate the rock away relentlessly, forming at first a large underground chamber and eventually a large sinkhole. Water from all the sinkholes feeding the Mammoth system flows into the ground and through the 350 plus miles of its chambers and passages. The limestone, which took 300 million years to accumulate, dissolved in a mere 3 to 5 million, and Mammoth is still growing. This is a karst landscape. The flat farmland is a sinkhole plain. The Mammoth Cave system runs under these hilltops. The hills are made of limestone, also called calcium carbonate. It is the remains of unimaginable numbers of prehistoric sea creatures, accumulated and compacted into stone over millions of years. Rain and surface water pick up carbon dioxide from the atmosphere and decomposing plant and animal matter from the soil. The water becomes a weak solution of carbonic acid. As it flows through cracks in the limestone, the acid dissolves tiny amounts of stone. Slowly, it eats away at little cavities. Some become sinkholes and vertical pits, funneling water from the surface into the ground. It flows downward toward the water table, following the fractures and faults in the limestone. As it goes, it eats out pockets, which eventually become passages and chambers in the subterranean bedrock. At Mammoth, the vast sinkhole plain adjacent to the hills funneled water into the ground. It flowed through the limestone toward the Green River beyond, carving cavities into passages and finally into the massive chambers of the cave system. It took 3 to 5 million years for this activity to create the hundreds of miles of Mammoth Cave. Then one day, a person entered the cool stillness of the cave, beginning thousands of years of exploration. Signs of human presence and passage through the cave are still where they were left 2,500 to 4,000 years ago. Archaeologists Pat Watson and George Crothers have been cataloging artifacts. The objects left in the cave only hint at what people were doing.
It's a climbing pole. It had been thought by some people to be a prehistoric climbing pole or ladder. We got a radiocarbon date on a little bit of the bark tie. The results that came back were 2,500 years old, plus or minus about 55. So it's for sure a prehistoric ladder.
Wood and other organic materials decompose in a couple of years on Earth's surface. Yet here in the cave, with little exposure to wind, rain, and the ravages of time, they last forever, proving that the early visitors were master cavers. Caving can be a hazardous endeavor. Why were early humans braving the deep unknown and entering into mysterious caves? Mining minerals is one answer.
This is sodium sulfate. It's one of the suite of sulfate minerals that we think the prehistoric people would have been very interested in. And if you put it in your mouth, it's definitely salty.
Tastes like salt.
The other thing it does, though, is it's a laxative. In the drugstore form, it's called Glauber salt.
The same process that carves out caves also decorates them. Rainwater absorbs carbon dioxide as it seeps through the soil above and around the cave, forming a weak carbonic acid solution. The acid dissolves limestone and carries it downward toward the cave.
As the water drips into the cave from the fractures and other pores that it's coming out of, it releases that carbon dioxide into the cave atmosphere because the cave atmosphere doesn't have much carbon dioxide. By releasing the CO2, it can't hold on to the dissolved mineral, and so it deposits some.
A stalactite is a formation that hangs down from the ceiling like an icicle. A stalagmite grows up from the floor. When the two join, they form a column. Formations grow fantastically slowly. In some cases, only 1/10 of a millimeter a year. This 40-foot-high flowstone formation may be well over 200,000 years old. Beautiful, eccentric secondary formations get names like soda straw and flowstone, names that conjure familiar things from the surface world. Fishtail helictites sprout from the walls as calcite crystals bond to each other. These are called draperies. Dogtooth spar, cave coral, and popcorn. Each is the unique product of calcite-rich water dripping, oozing, splashing, seeping into the cave chamber, and depositing crystals. calcite crystal formations aren't the only things growing and multiplying in caves. A specialized ecosystem has evolved in the darkness of the cave environment. It's not hard to understand why. There's no sunlight, nearly 100% humidity all the time, and very limited food. The annual range of temperature outside a cave may be 100 degrees Fahrenheit. Inside a cave, the annual range is more like 1 degree. Even cave air chemistry is different. The product of all these conditions is a community of creatures unlike anything found on the surface. At a cave's entrance zone, your eyes begin to adjust to lower light. The cool dampness and odor rise around you. Some cave species move in and out of the entrance zone, back and forth between the sunny exterior and darkening interior. Cave crickets, for instance, they feed outside and live inside. Move deeper into the cave, and your eyes dilate wide to gather the last of the exterior light in the twilight zone. Not many surface animals travel beyond this point, except bats. Bats hibernate in caves, others mate and give birth in caves, and others just stay overnight on migration. Bats are surface animals, but they depend on caves for survival. Beyond the twilight zone is the dark zone. Here we need lights to see, food to eat, clothing to keep us warm. Otherwise, we cannot survive. Other creatures call the dark zone home. These species have evolved to flourish in the total darkness of caves. Blind and pigmentless, they're completely adapted to the conditions of the deep caverns. The central character in the story of caves is water. Nowhere is this truer than in underwater caves. The state of Florida has one of the largest discharges of fresh water in the world. All of it comes out of thousands of miles of underwater caves.
Watch your step. Okay. Lift them up. Put them on the side. Right. Okay, we clear the sandbar? Yeah. Okay. Look for the spring when we get over there.
The entrance to Crystal Beach Spring Cave is just offshore of Clearwater, Florida.
All right. Get ready. Let her go.
It's a tidal cave with a strong flow and a very tight entrance. Not for the weak, and definitely not for beginners.
In cave diving, there's not a lot of margin for error. We try to be careful, try to make sure all our equipment's in good working order, do a lot of maintenance to it. We dive on a regular basis, and that keeps up our skills and our confidence level, and we just have fun.
Turn it off.
The unexpected can ruin the fun. An O-ring in Michael's regulator has blown out on the surface, not on the dive. If this had happened later in the cave, it could have been life-threatening. A simple problem on the surface becomes ominous in a cave.
Okay, we're back in business.
The Garmins must dive on the outgoing tide, which ensures clear fresh water and good visibility once they're in the cave. To get to the cave entrance, they pass through algae-rich Gulf seawater. The murk clears as they enter the lens of fresh water.
The entrance to Crystal Beach is one of the most difficult entrances we encounter in cave diving. We're dealing with tidal changes, visibility problems, and strong currents potentially at lower tides. We actually push our tanks in front of us and then follow them in. So we're breathing off a hose from a tank that we're pushing.
It will take them almost 45 minutes just to get themselves and their 500 pounds of gear into the cave. The extra air and equipment slow them down, but it may save their lives.
Cave diving is inherently dangerous because if you develop a problem or a piece of equipment fails, you can't just surface. There's a rock ceiling above your head. You have to think in terms of self-rescue and thinking through a problem. Almost any problem you encounter can be solved, but if you panic, you won't be able to solve it.
The Garmins are headed for a chamber called the Dragon's Lair. It's 130 feet underground and half a mile from the entrance. Here, the fresh water flowing out of the cave sits on top of a layer of salt water, like oil on vinegar. But the salt water isn't from the Gulf. It comes up from deep in the ground below the cave, and it contains dissolved hydrogen sulfide. The cloud is made up of specks of sulfur produced by bacteria living off the hydrogen sulfide. For Michael Garmin, the murky cloud is pay dirt. It was made by life forms that are alien to our world.
This is really exciting because the ecosystem in the Dragon's Lair, made up of amphipods, crayfish, other types of bacteria, may be all living off of the sulfur bacteria in there. So like on land, where plants and photosynthesis is the basis of the food chain, we may actually have a chemical synthesis and these sulfur bacteria as the base of the food chain. So they're creating a whole food chain without relying on sunlight.
How does this alternative ecosystem work? The Garmins have begun a systematic study of the cave from the bottom of the food chain to the top. And other microbiologists in the United States and abroad are bringing to light the strange and mysterious in similar hydrogen sulfide caves. They've discovered entirely new kinds of organisms, including a family of microscopic plants never seen or heard of before. Chemosynthetic bacteria, that is, bacteria that synthesize energy not from organic food, but from metals and minerals. Bacteria that may resemble the earliest forms of life on Earth, all living, growing, evolving in caves. Caves bridge the distances of time and space. They hold signs of our distant past and portals to the future. We don't have to go to another planet to visit a different world. It's directly beneath our feet, accessible, waiting in the dark.
You've been given all the information. Now it's your turn to discuss the questions. Take a moment to talk about the following.
How do limestone caves form?
Why is it important to protect caves and cave formations?
We hope you've enjoyed this assignment discovery analysis of the nonmetals. If you'd like to learn more about what you've just seen, go online or check out these books at your local library.